Okay, go ahead, Roman.
All right. Okay, so welcome everyone and welcome Mateusz. Mateusz is joining us again from Warsaw, and today he will talk about non-equivalent axiomatization of PA and Tarski boundary. And this is first of the two talks. There will be two modules, the first module today and the second module in March, a month from now. But all this will be announced in due time. So welcome, Mateusz.
Welcome. It's a great pleasure to speak in front of you. So I will talk about the results which are unpublished yet, but hopefully will be prepared for publication quite soon. So we are planning together with Ali to put them in a joint paper with some very nice results in the vicinity obtained by Ali also a while ago. Okay, so let me introduce the main character. So all these investigations will revolve around an axiomatic theory of truth and its extensions. So in the whole presentation, I assume that this fancy T is an RE theory in the language of arithmetic, which extends elementary arithmetic to have convenient coding apparatus. And L denotes the arithmetical language. And it is fairly easy to build an axiomatic theory of truth over such a theory. So basically, these axioms will be the same for all theories in the language of arithmetic. I mean, this is really a function of the language of arithmetic, but I mean, this notation CT minus of T means that we extend T with these axioms. So they are straightforward arithmetizations in this language jointly with a fresh predicate T of the usual Tarski inductive truth conditions. So let me quickly go through them. So the first says that atomic sentences are true if and only if, I mean, they are true according to the delta zero definable, that delta one definable truth predicate. And we may assume that the only atomic sentences are of the form S equals T. The negation of a sentence is true if and only if the sentence itself is false. The disjunction is true if and only if one of the disjunct is. And the existential sentence is true if there is a canonical numeral which substituted for the variable v in phi results in a true sentence. So note a few things. The first one is that I quantify only over codes of arithmetical sentences, but they are also arbitrary arithmetical sentences in the sense of the ground model. So in particular, in a non-standard model of CT minus over T, this predicate T behaves reasonably also on codes on non-standard formulae, and this is a partial reason for studying such object. And note that I do not add any induction for the language, for the language extended with the truth predicate. And this minus reminds us that we might not have induction for the predicate T. We do not add induction for the extended language. The induction might be present for arithmetical formulae. Yeah, so an abbreviation CT minus, abbreviate CT minus over PA. This will be our main focus during this talk. And also another piece of notation. So CTN denotes CT minus extended with sigma n induction for the full language, and CT denotes the fully inductive version of CT minus. So this is our basic theory. And now the main problem, I mean, it's, I think, the main research problem of one of the main research problems of our group in Warsaw. It's the problem of determining which extensions of CT minus are conservative over PA, more generally, which extensions of CT minus over T are conservative over T. The problem itself is non-trivial due to a well-known in this discipline theorem with, I guess by now, also 5 independent proofs, counting the recent proof by Fyodor Pachomov. So CT minus itself is conservative over PA, and more generally, CT minus over T is conservative with respect to arithmetical sentences over T, which means that it coincides on arithmetical, its arithmetical theorems coincides with the arithmetical theorems of PA respectively of T. However, upon adding a little bit of induction, this theory becomes stronger. So in particular, after adding delta zero induction, this theory is strong enough to prove the global reflection principle over PA with the assertion that all theorems of PA are true, and it is very easy to see that no such theory can be conservative over PA. And I will characterize its strength later on. So this is the problem for PA. Which extensions of CT minus are conservative over PA? And this boundary, which demarcates the conservative extension of CT minus from the non-conservative ones, is called the Tarski boundary. So the more the intuitive description of this, less mathematical but more intuitive description of this problem is what is the contour of the Tarski boundary, and this will be one perspective on the result that I will prove later on during this talk. So we shall get more informations about the contour of the Tarski boundary. Another perspective, however, is the finite axiomatizability of arithmetical theories in an extended language. So there is a well-known theorem due to Vought and CUNY, I guess, that every recursively enumerable theory which does not have which does not have finite models can be finitely axiomatized in an extended language. So it is very easy to see that. No, sorry. Let me start from the. Let me start once again. So it can be shown that CT minus over PA is not finitely axiomatizable, and in particular, this theory is reflexive, so it proves the consistency of all its finite fragments. So in particular, from this, we can deduce that CT minus over PA does not prove that all axioms of PA are true. because if it was the case, then clearly we would have a finite axiomatization of CT minus over PA by taking, say, CT minus over EA jointly with this one sentence, and it will be enough to deduce all the rest of axioms of PA, where this formula AXPA denotes the canonical elementary formula representing the set of axioms of instantiations of induction axioms. However, we can show that CT minus extended with this sentence is still conservative over PA. And in particular, in this one case, we obtain, in this way, we obtain a quite nice finite axiomatization of PA, quite nice, quite natural. So the this second perspective is to see for which theories CT minus can be used to obtain their finite axiomatization. So this is once again, this problem is non-trivial. Or let me consider the following variant of PA, the following re-axiomatization of Peano arithmetic, of Peano arithmetic. So this ref T is sometimes called small reflection principle for T. It is an infinite set of implications of the form if N is a code of a proof of phi in T, then phi holds. So by reflexivity of PA, one can easily see that, in fact, PA plus small reflection principle over PA coincides with PA. They are simply deductively equivalent. So let me take the natural representation of this set of axioms, PA plus small reflection principle. PA, I mean straightforward arithmetization. Let me add it to CT minus. On the left-hand side, you see this extended theory. The canonical, something which should supposed to be a canonical finite axiomatization of PA, and we can easily see that it does not work. So because, let me maybe show you, CT minus extended with a single sentence, every sentence from delta is true, easily derives the global reflection principle for PA via the following reasoning. Let me see, it will, oh, sorry. So we reason in CT minus plus for all x, if delta of x, then T of x. Then by arithmetic, it is very easy to see that for every x, since delta was taken as natural arithmetization of the set PA plus small reflection principle for PA, for every x and for every phi, we have delta of the following sentence, proof PA x phi implies phi. Right. So since all sentences from delta are true, then we get for all x and for all phi t of, and I will skip the proof. The corners. So such a sentence, sorry, this is probably redundant. Such a sentence is true in the according to T. However, this antecedent of the implication, this is a standard formula, perhaps on some non-standard numerals. And by applying commutativity conditions for the truth predicate, we get for all x and for all phi, if x is a proof of phi in PA, then phi is true. And this is the global reflection principle for PA. So, right, so in particular, some axiomatizations of a theory behave how to put it, behave reasonably, while others cause a blow up, and this is an example of this phenomenon. And this blow up is significant because CT minus plus global reflection principle for PA is arithmetically equivalent to the sum of all finite iterations of uniform reflection over PA. It is fairly easy to see that we can derive uniform reflection over PA in CT minus plus global reflection for PA, but we can iterate it, in fact, all finite number of times. So we have an example, we have one particular example when these axiomatizations behave reasonably. So in contrast, let me cite the following theorem. Whenever we have a schematic presentation of an axiomatic theory T, then CT minus over T plus all axioms, all instantiation of this schema are true. This theory is conservative over T, hence in particular is a finite axiomatization of T. So this was a reason why in the previous example of AXPA, we got a finite axiomatization of PA, while in this example, and the example on this slide above shows that I mean, it does not behave that nicely for all axiomatizations whatsoever. So let me see. So there are these two perspectives on the current theorems. The first one is the contour of the Tarski boundary. The second one is how unreasonably can such theories behave. So an example of a question is, suppose that we fix a theory T, theory T, and then study its various presentations, and then ask which theories can be obtained in this way. So these are the two main motivations for this research, and then a digression to to introduce some more information about the Tarski boundary. So this theory, which already occurred in the presentation, CT minus plus global reflection over PA, turns out to be extremely stable and admits various different finite axiomatizations. So let me introduce some of them. So over CT minus, the following are equivalent. Global reflection for PA, and I will use this short form T of a formula to mean that the assertion that all sentences satisfying this formula are true. CT0. So delta zero induction is equivalent, in fact. So we've already seen that that CT minus. So there are some questions on chat. Okay. Thank you, Ali, and sorry for yeah. So what Ali wrote on chat is correct. Sorry for not saying this. A schematic presentation of a theory results from a template which has a free second order variable, and we simply take all instantiations of this template with formulae of a given language. In such a way, an axiomatization of PA via an induction scheme is of this form because we take the instantiations of the induction scheme with all arithmetical formulae. Great. Okay, so quite surprisingly, over CT minus, this global reflection principle is equivalent to the sentence that all first order or all sentences provable in pure first order logic are true. So we don't need the truth of whole of PA, but it is sufficient to get delta zero induction, global reflection for PA, just the truth of all first order theorems. And the most surprising one out of this company, it's a straightforward generalization of the compositional condition of the compositional axiom for the disjunction from the axiomatization of CT minus. And this is, it says that every coded at disjunction over any coded set of sentences, if it is true, then there is a true disjunct in this disjunction, right? So in the list of axioms for CT minus, we had an equivalent for binary disjunctions, which by meta induction allows us to conclude that T really commutes with disjunctions of arbitrary finite length. However, here we say that it should behave reasonably with respect to junctions over sets of sentences of perhaps non-standard cardinality. And as shown quite recently by Cezary-Cieśliński and co-authors, this single principle over CT minus, one side implication, is enough to deduce the global reflection principle for PA. So the message in here, and let me maybe go back to this thing. The message in here is that if you draw the Tarski boundary then you know what is, I mean, one canonical theory which is below is CT minus. Its extensions, proper extension, is, for example, a theory which is still conservative, CT minus plus all induction axioms are true. Above Tarski the Tarski boundary, you have CT0, which is equivalent in the full language to simply to the assertion that if this disjunction over sentences from a coded set is true, then there exists phi in C, which is true, right? So conceptually, it is not that far from here to here. I mean, this principle, that was, in fact, that was our intuition in intuitions for a long time, that that this principle, I mean, should be rather weak, and it turns out to be to generate a significant arithmetical strength. So during the talk, we shall study, during the first part of the talk, which is scheduled that I plan for today, we shall be occupied with this region of theories which are provable in CT0 and above the Tarski boundary, and prove that, in fact, there is a family of extensions of CT minus, which is fairly natural, and you see what's, sorry, let me go back to the presentation, right? So, I mean, this concludes still the motivations for the talk and the background. So let me introduce first a piece of notation. So we shall study theories of the form CT minus square brackets delta, which means which will be finite theories of the form CT minus over the elementary arithmetic plus all sentences from delta are true. This is a single sentence. And we shall restrict our attention to internally correct axiomatizations of PA. So recall that if you two theories, and by this I mean formalized theories presented as, say, elementary formulae, so we say that delta is proof theoretically reducible to delta prime, or delta and delta prime are formal representations of some arithmetical theories, if this if the inclusion of the set of theorems of delta into the set of theorems of delta prime is provable in I sigma 1. So I sigma 1 can verify that really up to the deductive equivalence, delta is really a subtheory of delta prime, and we say that they are proof theoretically equivalent if they are mutually proof theoretically reducible, and henceforth we fix this PA to be the formula. We fix a canonical representation, a schematic representation of PA, and treat it as an elementary formula. And we shall consider only theories of the form CT minus square brackets delta for delta proof theoretically reducible to PA. Right? Okay, so I think I've said enough in terms of motivation, and we can go back to the proof. So observe that if we have such a theory, which is internally correct, then CT0, then it is a subtheory of CT0, I mean, CT0 proves global reflection principle for PA, and arithmetic in itself proves that whatever is provable in delta is provable in PA. Hence, whatever is provable in delta is true, provably in CT0, if delta is proof theoretically reducible to PA. Hence, these theories, they occupy this region around the Tarski boundary, which is below CT0 and above CT minus, and they do finitely axiomatize some theories. So in particular, this earlier example of PA plus local reflection for PA shows that there exists a delta which is proof theoretically reducible to PA, such that CT minus square brackets delta and CT0 coincide. Because we've shown that if delta is elementarily represents this theory PA plus small reflection for PA, then CT minus square brackets delta proves global reflection principle. Hence, it proves CT0. And the other direction is by the reasoning I've already given. Right, so this is, so we already know that using such deltas, we can axiomatize PA, and we can axiomatize also the theory of all finite iterations of uniform reflection over PA. And this theorem shows that, in fact, all RE theories can be axiomatized in such a way. So if we have an arbitrary RE theory T which extends PA, then the following conditions are equivalent. So this theory is provable in CT0, and we can finitely axiomatize T with a theory of the form CT minus square brackets delta, where delta is proof theoretically reducible to PA. So this is the main goal for today, and I will now move to the proof. So let me see that we've already done one direction. So for sure, if T can be finitely axiomatized by a theory of the form CT minus square brackets delta, then it is provable in CT0, because for every delta, CT minus square brackets delta is provable in CT0, in CT minus plus global reflection. So what is slightly more involved is the other direction. Given T, we have to find a delta, which is proof. Given T, we have to find a delta, and there are two things that we should take care of. The first thing is that this delta should be, say, internally weak, and this delta should be internally weak, i.e., I sigma 1 should show that it represents the set of theorems of PA. So we cannot simply take, for example, natural representation of T, because if T is, say, PA plus con PA, then this theory is not proof theoretically reducible to PA. And the second thing is we should care of is that we should hit with this CT minus square brackets delta, we should hit precisely T. So as we've previously seen, it is fairly easy to cause a blow up and to build a truth theory, a finite truth theory, which is arithmetically much stronger than T itself. So let me start with the discussion of how So it will turn out that it is fairly easy to guarantee this proof theoretical reducibility condition. What is more involved is to guarantee that the CT minus over delta will not overgenerate. And our method will consist in using the following observation of Bartek wcisło. So it can be shown that every model of PA admits an elementary end extension N with a predicate T which satisfies CT minus and makes true all the axioms of induction in the sense of N, and has the following peculiar property that each disjunction with a non-standard number of disjuncts is true in this model according to the predicate T. So you probably have heard about these so-called pathological satisfaction classes. So for example, already Kotlarski, Krajewski, and Lachlan gave an example of a satisfaction class which makes true, say, disjunction of sentences of the form 0 is not equal to 0. Here, this proposition pushes this still further, because in fact we can, in a single model, we can have that each such non-standard disjunction is true. And for the time being, to make sure I'm fine with respect to time, let me treat it as a black box and explain how we are going to use it in the main theorem. And then, if time permits, I will go back to sketch of the proof of this proposition. But what is also nice about it is that basically it is a trivial modification of the Enayat-Visser construction of non-standard satisfaction classes. Right. So there is an immediate corollary to this proposition. So, in fact, if we take a natural representation of an arithmetical theory T, then CT minus square brackets delta can be much stronger than T itself. However, we can easily find another representation of T such that CT minus over EA plus all sentences from delta are true is a finite axiomatization of T using the above property. So let me define the disjunction of length x of phi's. This is simply a disjunction which has x disjuncts, and each disjunct of the disjunction is phi. So let me define this generalized disjunction of phi, which is in 3, which is in here, to be the disjunction of length phi. We treat formulae as numbers. So in particular, phi can be thought of as in terms of its Gödel code. So we take phi many disjuncts, and each of them is phi. So why is this helpful? Is that this disjunction has finite length if and only if phi itself is finite. I mean, in a standard model, because this definition arithmetizes. So in a standard model, this junction has standard length if and only if phi itself is a standard formula. So let me continue. Then we take delta to be simply these generalized disjunctions over phis, and phis, they come from a fixed presentation of T. Sorry, I forgot to say that, I mean, T must be a recursively enumerable theory. So in particular, we can find its elementary axiomatization, and hence we can take delta to be simply this set of the straightforward arithmetization of this set of formulae, and to see why it works. So for sure, CT minus over EA, maybe let me turn to let me sketch the proof in here. Okay, so CT, if delta is as previously, so delta of phi, this is simply there exists a psi in a fixed elementary presentation of our theory T, so that phi is equal to the generalized disjunction of psi. And then for every axiom psi from this axiomatization of T, this is a standard, has standard length. In particular, CT minus over EA proves for such psi, proves that if such a disjunction is true, then psi itself is true, because this is just a finite disjunction. If psi is a standard formula, hence CT minus square brackets delta proves T, right? So it is, now we use this model theoretical argument to show that it is not stronger than T. So the conservativity right now, fix a model of T, and by the proposition find an N T models CT minus square brackets, sorry, a model of CT minus over EA, such that N is an elementary submodel of N. So let us fix on theories extending PA to make this all work. So assume that T is an extension of PA. This works also for weaker theories, but I stated this for the extensions of PA. So let me stick to this. And such that every disjunction of non-standard length is true in NT. So automatically such a model satisfies for all x, if delta of x, then T of x. Because either if x satisfies delta, then either it is a disjunction of standard length of some axioms of T, of an axiom of T, hence it will be true. Or it is a disjunction of no standard length, and each such disjunction is true in this model by the construction. So hence this model satisfies CT minus of delta, and this concludes the conservativity part because n was arbitrary. Okay, so I mean this is a corollary, and this is the method that we will use for these deltas not to overgenerate. I mean this corollary by itself does not have a direct link with the proof of the theorem, but it nicely illustrates the method that I will use later on. Right, so let me proceed to the proof of this theorem. And once again, I will try to write it because I hope it might be easier to follow. I will have everything written down on slides, which I think will be put on the website, so then you can consult them later on as well. Right, so fix. So given T, we have to find delta, which is proof theoretically equivalent to PA. So first, fix any elementary presentation of T. Fix any elementary representation sigma of T. And now we define. Define delta as a natural definition of the following set. So first, we take all the induction axioms to guarantee that that our delta is at least as strong as PA. And then we take something to guarantee that we hit exactly T. This something will consist of a set of implications which has as conclusion the generalized disjunctions over phis, where phi is from sigma, right? So this is for this delta not to overgenerate and to be as strong as t itself. But now we have to add something to make sure it is in fact proof theoretically reducible to PA. And this will be the antecedent of this implication. So we say that if theta is provable, we say that theta is a counterexample to reflection over first order logic, where theta is any sentence of L, right? So to the antecedent of this implication, we plug in something which is verifiably in I sigma 1 refutable in PA, because I sigma 1 can prove that PA proves reflection over logic. Okay, so we claim first, delta is proof theoretically reducible, equivalent to PA, and this holds since I sigma 1 proves for all theta, it is provable in PA that if theta has a proof in first order logic, then theta holds. So this is verifiable in I sigma 1. And in particular, from the internal perspective, each such implication has a refutable antecedent. So let's probe in PA. What else? So CT minus over delta is not stronger than T. So we call that T extends PA. However, to get this, we apply once again the same disjunction, the same model theoretical argument as previously. This is obtained so once again, if we have a model M of T, we find an elementary extension together with the interpretation for the truth predicate such that NT satisfies CT minus over PA plus all axioms of deduction are true. Right? So, and let me call it NT is disjunctively trivial. So it's every disjunction of no standard length is true. Right. So this condition guarantees that that all these sentences are true. And this condition guarantees that all these sentences are true as well, because they are all implications with true succeedance, right? Every such formula for arbitrary phi, standard for arbitrary phi, is true in this model, because finite sentences of this form are true because n is a model of t, and non-standard sentences of this form are true because n is trivial. Right? So this is the same argument as previously. So now we have to show that, in fact, this proves t. Here, the argument makes use of two fundamental logical tools. The first is reasoning by cases, and the second one is modus ponens. So first, let me fix an arbitrary MT model of CT minus square bracket delta. So if MT satisfies CT0, then by our assumption, T holds, sorry, this is a fatal error because, sorry, I'm using T in three different senses right now, for a predicate, for its extension, and to denote the theory. Sorry for this. Let me call this TH. I'm terribly sorry for this notational horror. So we now argue that CT minus square bracket delta proves TH. So we fix an arbitrary model of this theory, and if it is a theory of CT0, then M satisfies TH because we assumed that CT0 proves TH. If not, then the global reflection over first order logic fails in this model. Then MT satisfies. There exists theta, which is provable in pure logic, but false. Because the negation of this sentence is equivalent to CT0 by the previous theorem, by this theorem about different characterizations of CT0. So fix any such theta, and then MT, and then look, for this one theta, for which this holds, we have all implications which as succeedants have arbitrary axioms of TH. Right? So then MT, then for any axiom phi of TH, MT satisfies, it is, the following implication is true. If reflection fails on theta, then the disjunction, the generalized disjunction of phi is holds. So by the compositional conditions, we have if the reflection fails on theta, then T of the generalized disjunction, then T of phi. However, by the choice of theta, we have this. And applying modus ponens, we know that this disjunction is true. But this is just a finite disjunction. And each disjunct of this disjunction is an axiom of TH. So MT models phi, and we are done, because phi was an arbitrary axiom of TH. Right? So to sum up this argument, it was possible to prove it because there is an arithmetically very, say, simple principle, the reflection over first order logic, which is verifiably in I sigma 1 provable in PA, which in the presence of the truth predicate generates a very strong theory. That's the summary of this theorem, of this proof, and this was the main point of this presentation. And I missed a question in chat. Okay, see you, Cameron. Okay, so let me, so to conclude, this is just this argument. You can go back to it if you like. I will make the presentation available, and some corollaries about the Tarski boundary to conclude this presentation. So in particular, we know that in this area above the Tarski boundary but below CT0, there are, for example, two natural extensions of CT minus which are incomparable in terms of arithmetical consequences. One simply takes delta and delta prime to represent in this manner such that CT minus square brackets delta and CT minus square brackets delta prime represent incomparable arithmetical theories, finitely axiomatized and incomparable arithmetical theories. Moreover, if we have any arithmetically non-conservative extension of CT minus, hence any extension of CT minus which is above the Tarski boundary, then we can find delta. Sorry for the typo, there should be a delta in both places. We can find a delta that the CT minus square brackets delta is arithmetically weaker than this T. And this T is, sorry, is not necessarily, it's now not an arithmetical, a theory in the language of arithmetic, but a theory in the extended language extension of CT minus. And last but not least, we can find two representations of PA, two representations of PA, delta and delta prime, that at CT minus over delta and CT minus over delta prime, they are both, they are non-conservative. However, every theory which is provable in both of them is conservative in PA. One simply takes the appropriate arithmetical sentences, which are both not provable in PA, but their disjunction is provable. Okay, so that's all. Thank you very much, and I will continue with the second part in a month.
Okay, thank you very much, Mateusz. Are there any questions?
Yes, I have a question. This is Ken. May I ask a question?
Sure, go ahead.
Oh, okay. As I remember it in Vaught's old proof from years ago, he used the word pleonasm to describe this, what I think you're calling the disjunctive trick or the generalized disjunction. Have I got that right?
Here I do not know. So in fact, I didn't know that these disjunctions occurred also in the work of Vought. So maybe I'm just reinventing.
Well, it's just simply a question. I can't remember if Vaught used disjunctions or conjunctions, but this pleonasm, is a technical term, although it comes from literature.
Yeah.
The dictator says,
it's,
"Am I right or am I right?" That's a pleonasm.
It's. I mean,
Vaught used that kind of trick to get things to be enumerable. And I was okay. So that's
right. Yes.
Well,
Okay,
anyway, that's something to check out.
So I mean, so I'm sorry. So I'm sure that these pleonasms, they in fact they do occur in this Craig's trick, right? To get say
yes, you're right.
Recursive axiomatizations of RE theories and like p-time axiomatization.
Yes.
But this is something similar, but I mean, this is this long disjunctions, they are very useful tools in axiomatic truth theories, and they were already used by Lachlan in his proofs of recursive saturation from the satisfaction class. And
now, in the theorem where you have, I think the theorem you say is due to WCISTO. I don't dare try to pronounce it.
Yeah, it's a killer. It's Wcisło.
Wcisło. You have M. Is M countable?
No.
No, not necessarily.
No. But we can. I mean, we can move to. But we move to a larger model. So that's the idea. And this reconstruction, it works for general models.
Interesting. Thank you.
Thank you.
Thank you.
Mateusz, can you say a couple of words? What are you going to talk about next month?
Yes. So there will be a refinement of these tricks. So in particular, I'm going to look at the conservative side of the Tarski boundary. And there is one theorem which says something about various conservative extensions of CT minus of this form. Basically, it says that for every pi2 sentence, which is provable in CT0, we can find a delta such that this sentence is true on a definable cut. And in particular, in this way, we can get theories of truth extending CT minus with a very significant speed up over PA. So this is one thing. And the second one is the following family of theories. So, I mean, this theorem that I talked about tonight gives us a perspective on what's happening above the Tarski boundary. What happens below is slightly more complicated because, I mean, now by definition, all these theories share their arithmetical consequences. So we have to look at their truth theoretical content. And this is not that easy, but we can get the following picture. So there is a family of these deltas, of these presentations of PA, indexed by finite sequences of natural numbers, right, such that each of them, for each such delta f, ct minus square bracket delta is on the conservative side of the Tarski boundary. So if G prolongs f, then ct minus over G is proper extension of ct minus square bracket delta f. And if these two sequences, they are incomparable, then the sum, then these two theorems do not, then these two theories, they do not have a common upper bound below the Tarski boundary. So their, say, least upper bound is consistent. It will be shown that its consistency is provable in CT0, but it is not conservative over PA. In fact, we can build such an infinitely branching tree with omega levels decorated with conservative extensions of CT minus. So, but for this, we will need a refinement, in particular, a refinement of this model theoretical argument by Bartek. We will need to make one sentences, we'll need to build models which are disjunctively trivial for some sets of sentences, while they behave nicely for another set of sentences. So that's the idea.
Okay, thank you. Good. Any other questions?
Yeah, I have a question. There are a couple of times when you're analyzing these theories and sort of referring to these theories that are below CT0 but above the boundary, and I want to sort of hear how can you describe how you know that these are below CT0, or?
Yes. So we by our decision, we decided to stick to these theories of the form CT minus square brackets delta, where delta is proof theoretically equivalent to PA. And so this is this argument. So if delta is proof theoretically equivalent to PA, then in particular, I sigma 1 proves, hence PA proves, that what's provable from delta is provable from PA. And CT0 knows that everything that is provable in PA is true.
I guess my question is more the other way around. How do you know it's not equivalent?
How that they are strictly below CT0, right?
Yes. Yeah.
Because we can, right? Because we can pick T to be a theory, an arithmetical theory, which is strictly weaker than CT0, and we can finitely axiomatize it.
Is there like a natural example of something non-conservative extending CT minus below CT0, right? Like that's sort of,
I mean,
it's
so
nicely in that spot.
We are talking about this. I mean, in terms of arithmetic.
Yeah.
So then we have. Then hence we are talking about theories which are above PA, but below all finite iterations of uniform reflection.
Yeah, I see.
So I mean, single uniform reflection, uniform reflection iterated twice, pi2 reflection over PA, consistency of pi3 reflection over PA.
Right.
So this is quite, there are quite a number of...
right. The jump from PA to the first order consequences of CT0 is large enough that you can pick it a lot from there.
Yes. So,
right. Oh, that's great. Thanks. it looks like there's another question. Go ahead.
Hey, can I ask a question?
Yeah, go on.
Fine, thank you. And I'd like to thank very much to Mateusz Łewyk for very interesting talk. But I would like to apologize because I had appeared here about 20 minutes after you started your talk. And please forgive me, I beg your pardon. However, the title of the talk is Non-Equivalent Axiomatizations, yes? Of Peano.
Yeah.
What does it mean about the set of consequences of PA? If you take the inference rules, the modus ponens rule, and the generalization rule, and the set of the axioms A1, for example, and non-equivalent second axiomatization to this one A2, what about the set of consequences of such?
Sorry, so that's so that's a good question, and I owe you an apology because I forgot to say. So what do I call these non-equivalent axiomatizations? So recall this example, and the main theorem gives us a lot more examples. So you have, for example, what do I mean by non-equivalent axiomatization? So this theory is a re-axiomatization of Peano arithmetic. So ref PA is just a small reflection for PA. We can show that all such sentences, they are provable in PA. Hence, this theory is not only deductively equivalent to PA in the standard sense, but also verifiably in a very weak theory. I sigma 1, for example, but much weaker theories as well, is equivalent to PA. However, we can show that the truth of this theory, according to CT minus, is much stronger than the truth of PA. Hence, in a sense, the two presentations are non-equivalent on the grounds of CT minus, because we can have a model of CT minus where where all axioms of PA are true, but all axioms of this, but there will be a false axiom of this theory. I mean, so obviously, then in this case, this axiom will be non-standard, but in fact, that's the whole point of this research, that we do care about non-standard formulae. Everything which is a formula according to our ground model is fine for us.
Yes, but so as far as the Gödel's incompleteness theorems are concerned, these theorems hold for these non-equivalent axiomatized arithmetics. If you take, for example, such PA, Peano's arithmetic, axiomatized by non-equivalent ways, yes, as you have considered, then the Gödel's incompleteness theorems, first and second one, hold for this both non-equivalent axiomatic. Yes.
Yes. So I mean, so it is the case that, I mean, objectively in the real world, in the standard model, the two axiomatizations are the same. Moreover, they are verifiably the same in a very weak theory. But we can distinguish between them using this very weak truth predicate, by CT minus. But the Gödel's theorems apply in to
Many thanks. My final comment is That's why I have asked. I have mentioned Gada's incompleteness theorems, and my final comment is now a reference to a paper which I give.
I mean, sorry, you are muted.
Okay, so, I apologize. Okay, and this is my thank Yanis for the remark, and I have given now to the chat a final comment. There's a reference to a paper where a proof of the consistency of arithmetic system within the system is published. You, of course, you can have many dots. Yes, this statement can be seen very strange. Yes, but this is the information for you and for colleagues. Thank you very much.
I'll have a look on it.
Okay, look, so I just would a small question, Mateusz. So you compare theories using probability equivalent probability using I sigma 1 because it's strong enough. And you said that you can compare those. You know, once the equivalence can be shown probably in the weaker system. But would it make sense to compare them using stronger? Like, how about I sigma 2?
Yes, I mean, so I think that that's a good point. I mean, for sure, we will have more. For sure, we'll have more equivalent
Right.
presentations.
But they probably have to be somewhat exotic, right? Because
I mean, so the most I think that the simplest one, I think, is just let me think. For example, you can say that for every x separately, you can say that there exists a value of the Ackermann function on x, something which is which diagonalizes primitive recursive functions, and that should be already above. But in fact, in all these theorems, I made use only of the fact that it is fine if the equivalence is verifiable even in PA. I mean, it does not. I mean, okay, of course. I mean, it's obvious that it does not change the main theorem because there are more such deltas. So
right.
Already the smaller number was but.
No, I don't think it was a serious question, but I was just thinking about that whether you get something interesting if you go higher up in the hierarchy when you have comparisons.
That's a good question, and so far I didn't notice like any very interesting differences if you just put this this judge which verifies the equivalence of theories somewhere else.
Yeah, there's a whole hierarchy of theories one could use there as judges, and maybe there is some structured theory there, but I'm sure there is, but maybe uninteresting. No.
Yeah. So far I haven't discovered, and I mean this theorem, which I will prove next time. For example, it shows that. Let me go to it. that already if you have that already if this judge is I sigma 1, then these theories can have like even super primitive recursive speed up. And even, I mean, I guess that there will be super PA probably recursive speed up. So it, in a sense, I think that it's so far, I really didn't notice any serious differences between in the behavior of these deltas. If you just take, I mean, all say S12 equivalent or elementary equivalent instead of just I sigma 1 equivalent.
All right. Thank you. Corey, are you there?
Yes, hi, I'm here.
If I remember where you were speaking next.
Yes, I am. And I sent you an abstract, I think just shortly before the talk.
Okay. So
maybe I got it a little bit after, but yes.
So instead of explaining what you're going to talk about, well, let's encourage everyone to take a look at what they have to say. So Corey is speaking next week.
Yes.
All right.
I hope to see you all there. Thanks, Mateusz.